Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on December 8, 2025, about 6 days ago, and this paper tackles one-shot, real-time creation of photorealistic upper-body 3D avatars that stay stable over time. The key contribution is a system that fuses fast 3D reconstruction with a distilled video diffusion model so it can render high-fidelity, identity-preserving talking avatars at around 15 frames per second, instead of the minutes many video models need. The paper is titled ViSA 3D-Aware Video Shading for Real-Time Upper-Body Avatar Creation. And as we will see later, the results push real-time digital humans much closer to film-level quality. Alright, Figure 1 gives a visual feel for what the system actually produces. The leftmost column shows a single input portrait for each person, and this is the only image the method receives. The remaining columns illustrate real-time video shading, where each avatar moves through different poses and expressions yet keeps facial identity and clothing details. The sequences look smooth and consistent, which signals strong temporal coherence as the person talks or gestures. So while Figure 1 showed what the avatars look like, Figure 2 explains how the system actually creates them. The top pipeline represents the 3D reconstruction module, which lifts a single image into a canonical 3D Gaussian avatar using semantic, low-level, and learnable per vertex features mixed inside a transformer. The bottom pipeline then feeds 3D-aware features into a distilled autoregressive video diffusion model, which acts like a neural video shader to render smooth, photorealistic motion in real time. Well, Figure 5 compares self-reenactment quality across several methods using the same talking head clips. The leftmost column shows the original input videos, and each row gives a different person. The middle columns display champ, mimi motion, VACE, and GUA versus A, which often blur hands, distort faces, or replace backgrounds. The rightmost column shows this method, which keeps facial identity sharp, preserves realistic hand poses, and maintains consistent backgrounds across the whole sequence. So, while Figure 5 focused on self-reenactment, Figure 6 demonstrates cross-reenactment, where motion comes from a different person than the reference identity. The left columns show the input driving video and the still reference image that defines the target identity. The middle columns with champ, mimi motion, VACE, and GUA versus a frequently warp faces or lose identity as poses change. The rightmost column with this method keeps facial structure, expressions, and clothing details much closer to the reference, even under large pose shifts. Alright, Table 1 summarizes how different avatar methods trade off visual quality and speed. ViSA reaches the best quality scores, with the highest PSNR and SSIM, and the lowest LPIPS and identity distances, which means sharp, faithful faces and textures. GUA versus A runs fastest at about 89 frames per second, but with noticeably worse quality. ViSA still manages real-time performance at about 15 frames per second, while keeping quality clearly ahead of all video-based baselines. So after Table 1 quantified the gains, Figure 8 shows how the adversarial distribution preservation loss changes visual quality. The left column gives the target input images, while the middle column without this loss looks slightly washed out and blurry, especially around fingers and hair. The right column with the loss keeps sharper edges and richer textures, which makes the avatars look more natural and less synthetic. So, while Figure 8 highlighted quality gains from the adversarial loss, Table 2 breaks down where the runtime actually goes. The table compares feature-based conditioning against traditional RGB conditioning, measured in milliseconds per frame on a single A100 GPU. Feature conditioning removes the heavy encoder step, so total time drops to about 66 milliseconds instead of roughly 101. That reduction mainly comes from skipping the 36 millisecond RGB encode stage, which translates into a sizable real-time speed boost. So to wrap up, this work shows that pairing explicit 3D reconstruction with a lean video diffusion shader can give sharp, identity-faithful talking avatars that still run in real time. That combination pushes digital humans closer to everyday use in games, streaming, and telepresence. That is it for this episode of AI Research Roundup. I am Alex. Thanks for listening.